Manuel, welcome. We're going to be diving into some BOCK compressors today, learning about CO2. Me and Manuel have done tons and tons of videos together, so go check them out on LinkedIn. We met at Chilventa, AHR, and we'll see each other hopefully at AHR again this year. And we're going to just start talking about some technical things about the BOCK compressors, because this is what's very, very important, is really to learn the components and how CO2 is traveling through the compressor, but also each component in the compressor. This is key for protection from any dirt in the system, or capacity control when you have low load situation. What do you do? Because if you lose that oil into the system, how do you get it back? And understanding all these components are going to be very key to your success in servicing, installing, maintaining CO2 system. Manuel, how you doing, brother?
Hey, Trevor. Thanks very much. Good to see you in the new year, and very welcome here in Frickenhausen, online at the training center in Frickenhausen.
Yeah. I love it. Well, I'm going to go out there and visit you for sure, and we're going to hang out there hopefully sooner than later. But I love what the setup there. This looks awesome. Cutaways are one of the top things that I love. One of my favorite things about refrigeration is seeing cutaways. That looks like a beautiful cutaway there. How does the CO2 gas travel through the compressor? So we know that the suction gas is coming back. It comes through the service valve, but how does it actually, the gas go back to make sure it cools the motor as well as gets compressed properly?
Yes, we are coming in. You can see the suction shut-off valve here. We're coming in with the gas on the other side, so we can spiral here. And then we're going into the compressor in a central position. Here we have the suction filter, which we're going through, taking out any dirt when we have something in the suction line. And then we come with the gas in a central position, and a very good cooling effect we have in that position. And we're cooling the motor outside here, but also we're going between rotor and starter to take out all the heat what we're creating, and the heat losses what we're creating in the motor. More or less depend, of course. Bigger motors are more efficient, smaller motors are less efficient a little bit. And then we're coming up with the suction gas here in that position, and now I'm switching, of course, it's internally a connection here to the motor, and then we're going up here in the suction port here, in this chamber here, and then we supply the suction gas onto the different valve plates. And the valve plates are positioning here. We have a valve plate. Oh. Yes. Well. So what you can see is the valve plate is positioned here. It's a cutted compressor at the moment, so we have cut it away. But we're coming in with the suction gas in that position. So that port is coming from here, and then we're going up here to the suction port here, to the suction chamber on the cylinder cover. So the cylinder cover is then positioning in that way. We can see it here in that way. So we are now on the suction side of the motor, of the compressor, on the cylinder head, and then we can see here are the ports for the suction valve. We have in CO2 we have also some finger reed valves, which are a little bit rusty here because we're touching. But then we have the suction reed valves, which are on that position here, and where we're sucking in the gas. So they open because now we're moving down with the piston. You can see the piston is moving, of course. The crankshaft is driven by the electric. And we're sucking in the gas when the piston is going down. And of course, when we're reaching the lowest point, then we are starting the compression phase, and then we're moving and compressing the gas in that cylinder head. And then, of course, coming back to the valve plate, we have the finger reed valves here on the discharge side. You can see there are the valves are below this protection part here, which are limiting the stroke of the finger reed valve to open not too much, because then you would overbanding the valve. This is something what happens when we get liquid. Then we stress this valve on that position, and then we go with the gas. You cannot see that much, but we see there is a port here in that position where we go up here with the gas into the discharge chamber, and then we coming up here in that common chamber where we bring together the 2-cylinder heads, or maybe the 3-cylinder heads, depending on the cylinder numbers. And then we have the kind of pulsation damping system here inside to reduce the pulsation in the discharge side as well. And then we going out to the discharge to the system with the additional service valve here to have the discharge shut-off valve on that position, where we have also the options to connect our service equipment. And then we're going into the system.
Okay, and great. And so I like what you thought about that. Is that built in, that pulsation? Is that designed in the compressor, or is it in the service valve?
It's under the service valve. And we have, of course, there are different pulsation reduction topics. It's, of course, one is volume, what we can do, and the other is we can have some what we call impedance pipes, so to reducing pulsation further to make a compressor as smooth as possible.
Awesome. Can we go back to that other camera again? The one on the table. Perfect. So Manuel, so that's how it cools the motor, which keeps it efficient, running, and lubricated properly. What happens if a big gulp of liquid comes back, or you get a lot of superheat, low superheat, where liquid actually comes back? What's happening actually inside that compressor at that point?
I think that the first is, of course, the risk is when we get liquid and we have a high pressure drop here. It could happen very seldom, but it's sometimes also related to when water is inside, that could be creating ice here. But normally what happens when we have a gas phase still and everything is clean and dry, we can also have the liquid can damage the winding of the electrical motor. This is the first risk what can happen on the winding. But normally it's of course depend on the quantity of liquid. Normally liquid is going through the process, and then of course it's mixing with the oil. The oil system is something what we try to separate as good as possible from the refrigerant side. This is also the reason why we're closing our oil sump here and have not an open oil sump where the oil is covering the complete motor. So the oil is only in the oil sump in the front of the compressor here. And this is avoiding that we're mixing too much refrigerant with oil, and this is reducing our oil carryover. When we now get liquid into the compressor, of course, the liquid can take a lot of oil out of the oil sump, because we will mix also definitely something. But with the separation of the oil sump to the motor sump, we try to avoid that we get too much oil out with liquid, but also in general to reduce the oil carryover in the compressor. Because normally when we take oil with us, we take it out to the discharge side again. Best is when we separate a little bit oil and we get the oil back to the oil sump here and have it in the right position where it's needed for the compressor.
So when you don't have a lot of low, so it's not really bad liquid coming back, you just got a little bit like wet gas coming back, that's going to start to mix in with the oil and start to wear on some of the components, because that's what we worry about, that over time you wear like the journals or the piston or the piston pins or the bearing. So a little bit. But if you get a big gulp, your first step is you're worried about it washing or damaging the winding. So that could cause a short in the motor if you get a lot of liquid coming back really bad. Or what would that, because you said the first thing would be the winding to worry about if you got a lot of liquid come back. What would you see? Would it damage the winding, cause it to fail or short or something like that? Or
yeah, it can happen a short, that you have a kind of spot inside the winding where you have a shortcut then on the current on the electrical motor. And of course, what can also happen, it's a lot difficult to when you bring liquid to the compression part. So when you start to try to compress liquid refrigerant or too much oil, could be also a risk. then of course you get high forces during the compression part, because you cannot compress liquid, so you get very high forces which are somewhere have to go. And then it's of course with CO2, with standard refrigerants, we can see that a lot of damages can happen on the valve plate. Yep. With CO2, the valve plates are smaller, but we also see that there is a high load on the complete drive gear. So that's also, of course, creating load on the control, but also on the main bearings. And the main bearings are always, when you talk about main bearings, there are more or less two bearings. We have one bearing here in that position, and we have one bearing here in the front. And of course, when we're mixing the oil with too much liquid refrigerants, the viscosity of the oil is going down. And then we have here in that winding, that bearing here, we can see the first issue when we get the oil to the oil pump, and then we lubricating first this main bearing. And this is, of course, a risk that we damage the main bearings. What we can see in our compressors is always for CO2, we have not only the main bearing in the radial way, because they are more or less balancing the load which is coming from the compression, but there could be also when we starting the motor, for example, and we have sometimes also an axial load, and this is something what we have also axial bearings inside these compressors. And you can see this is positioning here and also on the other side. Because when the crankshaft is moving a little bit and the oil viscosity is very low, then you can get a risk that your crankshaft is moving into your housing more or less in this direction. And this is additional safety for CO2 systems. We have it also for hydrocarbon and other systems. We have this, we call it trust washers, where you can trust that you have also an axial safety on your compressor.
Okay, so that would be, so if you had liquid coming back or so CO2 over time and starts to wear that, you would start to see would you see the state or the rotor start to drop down or drag against the windings, or that would be the main bearing? So the main bearing wears, that would drop the rotor a bit and drag on the stator. What would the thrust ones do if they start to wear because of liquid refrigerant?
I'm not sure if I get you completely, your question, but I think when you have, of course, the main risk for wearing the drive gear is on the main bearings, but also on conrods, on the big end. Okay. Because there we're getting out the oil from the crankshaft. Maybe we can show it here. We can see the crankshaft, we're getting out the oil from the oil pump in that position. And then, of course, we're supplying the main bearings here. And you can see the other main bearings are here. And then, of course, we're supplying the conrods with oil on the different positions. And of course, there we have the highest risk because what happens is the liquid is in the oil. And then, of course, we're getting heat on the bearings, and then we have a degassing effect on the bearings. And this is a critical situation where we have no oil between the two moving parts. And this is, of course, a critical situation where you're creating moving parts need always a little bit of oil between to lubricate. And when you remove this, also with the degassing of the liquid, then, of course, you have no oil, and then the wear starts very quick because you cannot handle the big load what you have on the compression.
I love that term, degassing. I haven't used that before. I call it washing out the bearings and stuff. So you said that you separate the motor compartment versus the crankshaft compartment. Do you have like a check valve in there, or So what separates those compartments?
Of course, what we see is that we're closing more or less the different areas. So the motor is closed to the oil crankshaft here. Yeah. So this is normally, it's cut here, of course, but normally it's closed. What we need is, of course, we need the higher the pressure which is coming from the compression part into the crankcase have to go back to the suction side. And this is why we have here on top, you can see a special nozzle which brings the options that we get a higher pressure from the crankcase back to the suction side. But the oil is separated here. So when we want to have the oil back from the motor part, which is coming when we get oil from the suction side, then we bring it back here to the crank, to the oil sump.
What is the term you use for that top one? Because now that is dropping the pressure in the crank side, right? On top there, the valve on the top. What do you call that valve there? Yeah.
This is
yeah, that one there.
Yeah, this is a valve which is reducing the higher pressure, or gives an options to get out, to avoid that the pressure is increasing in the oil sump.
Yeah, so it's lower than the body. So you're always getting the oil coming back from the suction. So it goes into the crank. So your oil pump can continue to pump oil through the system.
But you always have a little bit higher pressure inside the oil sump normally. Because
do you?
Yes, because you have a backflow from the compression.
Okay, so you have a higher pressure in your a little higher pressure. So what would the pressure be? Is it like 0.1 or 0.2
yes.
0.1, 0.2 bar higher than the motor, the rotor side?
Exactly. Now when you stop then normally the motor, then you have higher pressure here, because then you have heat from the motor, which increasing the pressure here. And this is also then the options where you get oil back into the oil sump.
Okay, so but when you're running, you're actually your compression, your piston side or your crank side is actually a couple points higher in pressure because of that valve on the top. Is that correct?
No, the valve avoids that you get a pressure balance between oil sump and suction side. So you have to take out the higher pressure from your oil sump, because when you close that space here completely, that area, then you would increasing the pressure further and further. And this is something what you avoid. And this is taking care of the valve here, takes out the pressure from, let out the CO2, which creating the higher pressure here, and takes it to the suction side. And of course, with this effect that we have a suction gas flow here, you can take out the oil the higher pressure on the oil sump.
So now we have an overheat situation, and we wore the cylinders sleeves, and now there's blow by happening. We actually, every compression, we have discharge going into the crank there. What happens to that oil? And what can technicians see when if that's the case? You overheat, you damage the cylinders walls, and the discharge actually is not going out the discharge anymore. A percentage of it's going into the crankcase. What would a technician see?
Yeah, that's a little bit a question how strong the damage is already, because I think you will not realize it in the beginning when it starts. You will of course see an increasing power consumption from the motor side, because you have a higher torque on your drive gear when you have wear maybe in different positions, because then you're increasing the load on to move your crank drive gear here completely. And this is of course something what can realized. And then of course you will see that the discharge temperature is increasing. Of course, also when you may be creating a bypass or something, so depend on how strong your damage is. Maybe if you already have damaged some valve plates, because what happens is, of course, when you have liquid sluggings, you can really also damage a complete piston. And then, of course, the piston parts are moving into everywhere. So you have it in the cylinder liners, you have it in your valve plate. You damaged a lot of things. And this is, of course, always a little bit the critical situation. When do you realize it? But it's a little bit dependent on how quick it happened. When it happens in a very short period, then maybe no protection will react that fast. But of course, it's what I already mentioned. You can implement it as PDC sensors on the discharge side. So when you have a damaged valve plate or something, not under all conditions, but quite often they trigger the compressor and stop the compressor before maybe you damage the complete compressor, and maybe you can you can help the compressor when you're changing the valve blades or something, because this is easy. You can remove the cylinder head and then you can change or put a new valve blade on. But it's of course a little bit, when you do that, you have to check what is damaged really. Can you see sometimes also, for example, when what you mentioned, when the overheating is too much, you really can welding in the piston or the piston rings, and then the complete piston sticks in the cylinder liners, and then the forces depend on how the compressor is running in that conditions. And you have that high forces that you also can damage really the compressor completely. But sometimes the compressor is running for a while, and then of course there happen a lot of strange things inside the drive gear because you damage so many things. In the end, it's very difficult to see where it starts. But when you see there is where something, then you can really welding some different parts together, and then the forces are very, very high.
Yeah, exactly. Can we do a couple of close-up shots on the oil pump side? So where you guys put in the oil pressure? Yeah, change camera. Yeah, just pull it over. We'll do some. So great. So on the oil pump side, where would the technician put the gauge on for checking the pump pressure again, so we can get a close-up?
Yeah, this is a little bit difficult to see now because we cut it away.
Okay, but it would be
another one.
Yeah, that's perfect right there. So I can see where the access fitting would be. Yep. Okay, beautiful.
See where I put another oil pump here. What you can see, there is a connection where you have the option to connect and measure the oil pressure here.
Yep.
And this is now only the part where normally is connecting the oil differential pressure switch. You can see here. You can use the electrical part. There is an adapter in, which is screwed in, which is measuring on one side the crank, the oil sump pressure.
Can you lower it a little bit? Sorry, Manuel. Can you lower it just down? Yeah, there you go.
Exactly. So this part is measuring on one side the oil sump pressure, and on the other side it's connected with the oil pressure, high pressure after the oil pump, and then there's a small piston inside which is moving then, and when you're reaching the low with differential pressure of 0.65 bar, and then you get a signal with the electronic. Now we reach the lowest allowed differential pressure, and then we trigger the compressor that we switch on.
Is it a gear? Like, what does the pump look like on the other side? Can you turn that around, or is it in that?
It's a gear.
On the one that you have in your hand, is it on there or no? The pump.
Yeah, it's you cannot see it because it's
okay.
But we can take a look with the camera here. Good. Where is it? Here. It's difficult with the camera. Yeah. There is a gear pump with.
Yep.
You can see it a little bit.
Okay, perfect. Can we do a close-up of the capacity control now and just walk through that like a closer view on how that works? So yeah, that as well as the head, if you have the head there as well.
Yeah, it's a little bit we have not a mounted one.
That's okay.
But yeah, it is what we are doing, and I think this could be maybe a quite interesting with the video what we published, because what we have with the capacity unloader here, we're doing not a block suction. What we call block suction for synthetical, what we're using. Yeah, we stopping the suction side, so we're closing the suction port on the cylinder, and then the compressor cannot take in suction gas, so then it's unloaded. With the CO2, we have another technology because it is too sensitive with the higher pressure to have a proper condition or working condition all the time. So what we are doing with CO2, we more or less really unloading the complete cylinder head. We do a kind of bypass system, and we have a non-return valve also installed in the compressor, which are stopping that we get gas back from the high pressure side, from the discharge side, from the gas cooler side. And then the advantage is With the unloaded cylinder cover or cylinder head, we're reducing the discharge temperature a lot, and this is reducing also the risk that we overheating the controlled cylinder head. And this gives a lot of possibilities to make a longer unloading, but also to make this high frequent flex control system in a more efficient but also more reliable way. This is the advantage of the technology what we're using for CO2, and it's a little bit different to what we're using in synthetic flow.
Yeah. Can you flip it over? Can you see any of the holes on the head itself, or you can't?
Yeah, what you can see is, of course, there is normally here, there is a piston inside in that cylinder head here. There's a piston.
Oh, okay, yeah.
Which is closing and opening a connection between the suction and discharge side. Now it's going, I cannot get it out. And then of the other side, you can see, of course, not that much, but
lower down, just put it down lower. Yeah.
You can see the different ports which are going from the high pressure side to the suction side. This is high pressure side, this is suction side. Yeah. And there is a connection here. It's not so easy to see. Yeah, but it's the port where we open. And then we have a connection between the two ports. And there are, of course, some holes inside which are opening and closing the valve when we have actuating with the solenoid.
So as you energize it, it will change. It'll open or close, and using the discharge pressure to move that piston.
Exact. And the discharge pressure will. So we open a small nozzle, more or less, and then there is a connection from the high pressure side to open the piston inside the valve, and then it opens, and then we have unloaded more or less the cylinder head, and then we have, of course, reduced the capacity with 50% or 33% in the 6-cylinder, and this is something what we can influence when we're closing and opening the valve in a way like we want to do it, and how we want to balance and control the unloaders. So this is the principle, and it works quite good for CO2 in that way, and very reliable, and with the high flexibility what we have then.
Could we pull up the Danfoss oil level control, because you got a port on it? Yeah, so we have a couple closer up shots. So just talk about why you have that the backing on it that goes into the compressor, and just a couple, if you want to talk about a few of the features.
I think what we can see here is with this kind of pipe, what we go into the oil sump, it's of course inside the middle of the side class we normally want to have the oil. So that's the optimum oil level in the compressor. And what we have with the pipe here is we calm down the area inside the oil level regulator, because then we can avoid any influences from foaming or degassing effects, so all the turbulences what we described in the beginning of the conversation also. This is something what we can avoid, and then of course we have a smoother control and a better options to measuring the real level inside the oil level control. And this is, of course, there are different options how to control, not to overfill the compressor, not to have too less oil. So there are different control principles which helps to make the oil management and the oil return to the compressor very smooth, and not too extreme reaction on the oil level regulator. So this is a very dynamic and smooth operation when you have the control in that way. So we can inject the oil here, bring it back from the oil management system, from the oil separator or from the oil receiver, injecting here directly to the oil sump, of the compressor, and then it's a very smooth injection also, that we do not creating too much turbulences inside the compressor, which could creating again higher oil carryover in the compressor, what we want to avoid as well.
Is there a filter on that flare there, or on the inlet? Do you guys have filters or no? I just want. So right there when you're touching, is there a filter there or no?
That's a good question. I think so. There is a filter, yes. But I'm
just on the brass.
I think the filter is the filter is recommended to do inside the oil rig.
Okay, good. I just want to know that.
But it's, yeah, exactly. It's also important, of course, the nozzle which is going in, that you can really also the injection time to really balance that in a good way to get not too much oil, but also not too less oil, so that the opening time is reduced, and this is balanced. But it's, of course, for the nozzle, it's important that you did not get any dirt back maybe from your from management system, and that is why the filter is important, because it's a smaller nozzle. I do not know exactly, it's 0.8 millimeters or something around, but I do not know exactly. I have to check.
Could we do a close-up shot again of the two different pistons? You had a 404, I think, piston versus the CO2 piston, the difference in the size of it?
Yeah, I think this is what you can see. That's the smallest piston what we're using on Transcritical compressors, 28 millimeters. And then you have here the piston for CO2. It's around, when we calculate, this is around 5. When you consider medium temperature conditions, then we have around 5 kilowatt cooling with each piston. So this for CO2 and this piston for 134A, same capacity.
Well, it's a,
but this is the high volumetric refrigeration capacity what we have with CO2, and it of course helps a lot when we consider the pressure difference. When you have a high surface like this, you have higher forces, of course, on your complete drive gear behind, and this is of course important to consider this also here. You have CO2, we handle here a discharge pressure of up to 130 bar, and the differential pressure between the suction or the crankcase oil sump part here, between the high pressure, it's up to 105 bar differential pressure. What we is.
I do have a question too. So what happens if you have a very low differential pressure? What happens to the valves, like the suction or discharge valves? And is there a limitation on the CO2 on how low you can go with the differential pressure? Because I know if you get really low, I would say 4 or 5 bar, the valves will start flapping. Do you guys have a limit on that, or? Because we know we don't want too low of pressure ratio or compression ratio.
Yeah, I think that more limitations in the envelope, we do not go that low, because it's also something what is difficult to test, and it's the same in the system side. It's also, you have to manage that low differential pressure on your system side, because you have to take care that your expansion valves, maybe your high pressure control valve, and the different steps what you have in a CO2 system can handle that small differential pressure. So it normally should not happen in the compressor, but of course there are some conditions. But I think it's of course when you have smaller mass flows, but also when you have very small differential pressures, that you can influence the running or the operating conditions of your valve blade that's influenced on that. But I think this is normally not such a big case, because quite often the limitations are given from the system side and from your valve in the system side, which minimum differential pressure they can handle to work from.
Manuel, this has been awesome. Like I could keep you here for another 3 or 4 hours and ask you questions. So Manuel, how can people get a hold of you, learn about the training center, learn about you if they want to learn more about BOCK and dive into this a little bit more?
Yeah, I think we can, of course, what we offer is a lot of trainings what you can find on the Danfoss webpage, and of course there is a part where you can find when you put into Danfoss BOCK compressors, then you see a lot of information. So you can find a lot of our selection software, but you can find also a training part where you can check the trainings which are maybe what we planned for 2025 this year. So you please feel free to check this. What we also have, of course, are the different YouTube channels where you can find a lot of information about compressors, all the topics what we discussed, maybe with some animation behind, so to understand maybe the flow a little bit better in that way. Also, of course, what we discussed with the capacity regulator, we released just last week a new video about how the principle works and learn a little bit more and understand a little bit more about this. And of course, it's always open to contact your contacts in the different countries. That was sales organizations. They are everywhere in the world, and of course, I'm happy to support also with questions from them, or questions from any kind. And then of course, we can go in contact and see how we can support trainings or deeper insights on compressor and
Love it.
other components. What we have, compressor is only one part of Danfoss. Of course, you know, Danfoss, big world of CO2 components, other components, valves, ejectors, filter drivers.
You guys got tons of stuff. Just endless. Manuel, this has been awesome. This has been awesome. I learned a ton from you. I definitely need to get out there and come and visit you guys and do some videos with you there. So thank you for taking the time to do this. I will have my team. I'll go through it. We'll cut it up. I'll send you some copies so you can see it and stuff like that as we share it out. But I really appreciate you taking the time. This is a lot of fun.
Thank you for having us. And it's always nice to have discussion. And also what I like is always to get feedback and get a little bit insights also from your learnings. That's always good to have this exchange a little bit. And I think I'm looking forward to see you in the AHR. It's not that far. Huh? It's very close.
No, it's just a few weeks away.
And everything. So yes, the hotel I have, but the flights I still organizing a little bit the agenda around what I like to do. It maybe I have the chance also to visit our colleagues in Tallahassee with the turbo core compressors. It's the first time I want to be there also to see the colleagues there, because they belong to the same commercial compressor group in Danfoss, where we have.
How long are you going to be in Orlando, or like how long are you going to the US for?
Maybe one week around. So I will be arriving on Sunday maybe, or maybe already on Saturday. I don't know exactly. And then I will see if I have the chance to go to Tallahassee also. At least we will be there for the exhibition. And
well, I'll see you there. I got a time booked with Danfoss, so we'll probably do some more videos while we're there. Hopefully, I'm there for like 10 days. I got 3 events back to back there, so I'm just like, I've been there for too long. But yeah, this was awesome. I'd love to do some more stuff like this with you. I know lots of people are going to love this, and I learned a ton. So now I can share a lot of new stuff and even terminology that you use that I don't use. I love the degassing one. Like, I know it makes sense.
Sometimes maybe I'm not a native speaker. You know, sometimes we're using words maybe we creating or whatever, but it's a little bit
but it's so true. Like in the oil, because this is about propane. You know, when I do propane training and I'm starting to do more, it's like in that oil there's propane. So now as it's degassing out of the oil, you know, it's boiling out of the oil. Now that's an issue. So that's why you got to get nitrogen through there and blow that out to make sure it's all gone before you put a torch on it or anything like that. So it's
exactly it's a high risk for it's interesting. Do you think it's hydrocarbon getting an issue in the US market? Do you think this is really
it's all regulation?
Some companies are doing something, but
like True Manufacturing, they do. I don't know if you know who they are. They're a case self-contained. They turned rate the propane 10 years ago almost. You know what I mean? So there's tens of thousands of units out there, but nobody wants to work on them, right? So it's just kind of like if something happens, they just get a new one and they just, they replace it. Now for the larger systems, there's a lot of rules and regulations here in North America. So industrial sites, like some of my buddies, they said, Trevor, I've been using propane since the 80s, hundreds of pounds in systems, but now it's like it's worry. Oh, I can't use propane. It's very dangerous. But you guys, they build the system safely. So there's a lot of rules. I see some systems right now. There's one in California that's been there for about 8 or 9 years, where it's propane on the roof, and then they're pumping CO2 through all the store. So like a secondary, an overfeed system, a CO2 system. I'm hearing a few more about the larger one, but not much. It's all small stuff at this point.
It's interesting because it's the same a little bit in Europe. There was a long time just very few players. now we see, maybe you saw on the Chilenta also, they're popping up more and more, especially in chiller applications, of course, which are located out. Also, we have a lot of discussions about heat pumps at the moment with the heating industry. Of course, there's a big discussion in Europe about this. And also when we talk about high temperature heat pumps, this is, of course, sometimes
we could do a whole session on that
for high pressure lifts. But when you have just a normal heating request, then hydrocarbon fits much better than CO2. And this is something we installed here in our factory. And maybe when you have the chance to come, we can show you. We have different chiller systems here for our test lab. We have everything cooled with hydrocarbon, with propylene, yeah. And then we have our air conditioning system is also a propane system, where we have 135 kilowatt cooling capacity, which we are doing also with hydrocarbon. They are located outside, so we're going with glycol system into the building, so the risk is limited just to the chiller side. But it's still a challenge, of course, here, and then a lot of companies are afraid of what the risk management and how they install, where they install, and how to do service. And I think they're starting normally the risk not from the manufacturing side. Is you have everything under control, but to train the people how to work with
I think we should do a whole session on your compressors in a heat pump application, because that's a whole nother topic. I could spend 3 hours just talking to you on that. Like, what's the temperature coming back? What's the max you can get? What's the kilowatts? And different applications going to be different. You know what I mean? What's that return water temperature, and what's the limitations? And so there's just so much to talk about. So I love it. I love it. I think this is great. I think there's a lot of knowledge here shared. Excited to see you in a couple of weeks, and I look forward to connecting with you in Orlando.
Okay, perfect. Thank you very much.
Thank you so much.